Hello everyone, my name is Pawicha Phairatchatniyom. I am a lecturer from Rajamangala University of Technology, Krungthep, IMUTK, Bangkok, Thailand. Today I am going to present the golden ratio algorithms with new step-size strategy for variational inequalities problem with application to sparse logistic regression. This is my online presentation, the first one. In this study, we consider the variational inequality problem, which is defined as inequality number 1.1. Here, we are going to find H in S, which is a finite dimensional Hilbert space. A is Lipschitz continuous and monotone mappings, and F is proper convex and lower semi-continuous function. We use S VIP to denote the solution set of our problem 1.1. In the case that F is the indicator function of the closed convex subset C of H, then the variational inequality 1.1 reduced to classical VIP, this inequality problem. And we know that variational inequality problems are very important because they have many applications, such as in the optimization problem, economic problems, or engineering problems. For example, to solve the VIP 1.1, Malitsky introduced the golden ratio algorithm GRAAL with the constant step size defined as follows. And you can see sequence yn and Sn defined as 1.2, which is lambda is a constant step size belonging in this interval. However, constant step size are straightforward and difficult to compute because they require the parameter of the Lipschitz constant, and this may cause the algorithm converge slowly. To improve this, Malitsky proposed adaptive golden ratio algorithms AGRAAL using self-adaptive step size strategy to improve the algorithm, which is improved robustness and conversion efficiency. The sequence use self-adaptive step size lambda n defined as equation 1.3, and you can see this is a new strategy. And then we compute sequence yn and n as defined in 1.4, and you can see now this is a self-adaptive step size lambda n. Next, time and data investigate the Bremen modification to algorithm of Malitsky 1.2 with both constant step size and self-adaptive step size. With the constant step size, it called Bremen golden ratio algorithm BGRAAL, which is defined as a sequence by n in the 1.5, and you can see this is a step size, constant step size belonging in this interval. In the case of self-adaptive step size, the sequence lambda n defined as equation 1.6, and you can see this is new strategy, and this is the sequence by n and n which use self-adaptive step size lambda n. they point out that the algorithm have an advantage in the flexibility of the Bremen-Prosmal operator. In the particular case that in the convex games, it can correspond to projections onto the probability simplex with the closed form expression under the Quebec-Libre divergent. Unlike the Euclidean case, however, in the constraint optimization, an appropriate choice of a Bremen distance can incorporate the constraint set into the domain, thereby ensuring feasibility of the iterative implicity. Recently, Yao et al. Proposed new algorithms with both constant and self-additive step size. With the constant step size is called strongly convergent golden ratio algorithms and given as sequence by n, which divided as 1.8, and you can see now this is a constant step size. With the algorithm with the self-additive step size, it's called strongly convergent adaptive golden ratio algorithm (STAGRAAL), which is defined lambda n as 1.9, and you can see this is new strategy, and the sequence by n defined as 1.10, and you can see this is the self-additive step size. Yao et al. Note that the algorithm obtain the strong convergence in the Hilbert space with both the constant and adaptive step size, and the algorithm has good numerical performance compared with the existing methods in the literature. Motivated by the above result, we propose algorithm with both the constant and self-additive step size to solve variational inequality problem. We consider with the initial extrapolation to develop the algorithm converging faster. And we also consider the stability of step size, which is remove the need of Lipschitz constant of the monotone E, and we also obtain the strong convergence with the suitable condition, and our algorithm has good numerical performance. Next session, we are talk about our main result. This is our first algorithm. We use constant step size, and we call it adaptive strongly convergent golden ratio algorithm (ASTGRAAL). And the algorithm use initial extrapolation, which is theta n defined as 2.1. And after that, we compute by n in the sequence defined as 2.2. And now you can see our algorithm defined using MAN algorithm. And this is our sequence xn. In the case that the self-additive step size, we call adaptive and strongly convergent adaptive golden ratio algorithms ASTEAGRAAL, where the self-additive step size lambda n compute like sequence number 2.3. This is, you can see, this is new step size strategy, and this is our sequence yn an. We choose MAN algorithm and self-additive step size. In In the proof, we need this assumption, that is, we assume that the solution set is non-empty. A is a Lipschitz continuous and the monotone mapping, and F is a proper convex and lower semi-continuous function. And then we will get the strong convergence theorem for both algorithm 2.1 and algorithm 2.2. Now we are talking about our numerical experiment. First example, we consider this example, which is hyperspace is equal is a L2 space, and this mathematical symbol is mean the consisting of a sequence with finite many natural terms, or you can see this definition. Ax defined as follow and is both the monotone and Lipschitz continuous. Okay, to ensure fair comparison, another algorithm, we take the function g or f in the definition of the proximity operator to be the indicator function of a set C, where C is the set of S that satisfy the condition that norm x less than or equal to 4. And we compare our algorithm 2.1 and 2.2 with the set algorithm that we already mentioned in the section of introduction. And we set our parameter as follows. Since we have various parameters, so we skip the value of the value of parameters, and we randomly generate the initial points for each algorithm and set the stopping criteria En, which is stop when it's less than 10 power minus 7. The result of this is our result, and you can see that our algorithm number 2.2 has a good performance compared with the other algorithms. And this is the graph of error E versus the number of iteration for n equal 100 and n equal 900. Now going to the application to the sparse logistic regression. The sparse logistic regression problem defined as the problem number 4.1, where AI is denote the features vectors, BI are the corresponding class labels, and Z is a regularization parameter promoting sparsity. This problem is widely used in the machine learning for learning linear classifier with sparse coefficients. And next we define matrix M by Mij equal minus Bi multiplied by Aij, where the induced function had df by defined like this. And then our problem 4.1 can be expressed as the J of x equal the addition of D of x with the F of x. Okay, and we will get the Lipschitz constant equal 1 a quarter, and Lipschitz continuity of a composite function equal a quarter multiplied by norm of transpose matrix M multiplied by matrix M. And we compare our algorithm 2.1 with the proximal gradient method and the first iterative Chingate thresholding algorithm of ISA. This is the setting of all algorithms, and the algorithm stop when is this norm less than and you go to 10 power minus 14. This is the algorithm. This is PTM This is freestyle and this is algorithm 2.1. Discussion. The proposed framework is a bit in the hyperspace, so it's a good idea to attend to the banana space or more general relational inequality problems. Deriving implicit convergence rate under additional regularities such as strong monotonicity or aerobatic condition would further strengthen the theory. Okay, and it would be also be of the interest to incorporate multi-step of alternate initial terms and develop solve that is variance with to large-scale problems and apply the algorithm to the image restoration and signal recovery would help compound the robustness and practical efficiency. This is some reference. Thank you for your attention.